So we're going to get started. Welcome everybody to the scientific methods for grades 4 to 6 in the new curriculum. So just a little bit about who you'll be spending the next hour and a half with. In the background is Ted, and you may have gone to his session yesterday. He's going to be monitoring the chat for me since there's quite a few of you registered. And so I may pause at certain points, but I will have a question and an answer period at the end because, again, there's a lot to get through. My name is Nicole Lamoureux, and a little bit about myself. I'm the designer professional learning consultant, or one of them here at the consortium, the Alberta Professional Learning Consortium. And I have over 20 years of teaching experience in the elementary classroom setting. I also served as the elementary science consultant with Edmonton Catholic School Division. And I just recently completed a 2-year secondment at Alberta Education. So I've got some sort of insights and things to share with you along the way. Okay, so we'll begin with the treaty acknowledgement. In the spirit of reconciliation, we want to acknowledge that this gathering is taking place on traditional lands across the province of Alberta, home to many diverse First Nations, Métis, and Inuit peoples. We acknowledge that this land is a traditional meeting ground, giving voice to its original peoples and the story of creation of this country in a way that history has forgotten. So the agenda for today is we're going to spend the first 10, 15 minutes kind of situating and providing context about science as a discipline, because we haven't had a lot of professional development in the area of elementary science. So just kind of a little bit of background that'll help us understand the curriculum in this scientific methods. And then we're going to do some unpacking of the methods itself. So there'll be some processing work in a program called Lumio. So it's pretty straightforward. I used it in the last symposium and it was pretty easy for most participants. And then, of course, we're going to look at some classroom examples. What does this look like in our classroom? I think many of you want to know that. And also, I get asked the question, the resources will be translated in French at some point down the road. Okay, so to begin with, we're going to look at, well, what is science? What is the purpose of teaching science and the purpose of this discipline? Well, science itself is the study of the natural world to investigate phenomena. And phenomena is just a scientific word for an event, a situation, or facts that make you ask questions. And I think as human beings, we are naturally curious. And so science provides these methods or attempt to way of answering those questions. Why it's happening, how does it work? We have a virus. It seems to be a little bit more complex than a flu. It's causing some people to be really sick. And so what is it? How does it work so that we can understand it and, cure it? But not only is science a subject that we study in school or post-secondary, it's something that confronts us as citizens on a day-to-day basis. For example, should I mask or not mask? Vaccinations. Should I vaccinate or have my children vaccinated? Science seems to be changing its mind. That comment sort of can reflect a lack of understanding of science and how it continually refines its knowledge over time. Not only that, our students are going to be faced with issues that they're going to have to make informed decisions about, such as global warming. If I know that we're here today and we want to understand our grade level and we want to unpack that right away, but I really encourage us to kind of take a step back. And if you haven't read the curriculum subject introduction, I encourage you to do so because it does give some insight about the curriculum and the purpose and how to teach it. So for example, it says, scientifically literate citizens are equipped to evaluate sources of information encountered in daily life. So we want our students by the end of grade 12 to be scientifically literate so that they can understand when they hear things in the news, what it means. So if we're going to do that, we should know what it means to be scientifically literate. And PISA, the Program for International Student Assessment, defines scientific literacy as being competent in 3 areas of science. So we have our first, which is content knowledge or conceptual understanding, or like the big ideas in the different disciplines in science. So we have physical science, which is like matter and energy. We have our earth and space sciences, which are systems in our curriculum is the same. And then we have biological sciences, which is like living systems in our curriculum. But in science, we have scientific methods, and those are the procedures of getting that knowledge and understanding. So we want our students to know how an investigation works by doing it. And I think we're familiar with that. What's kind of new in this particular curriculum is something called epistemic knowledge. And that's just a fancy word for understanding. So if they hear on the news, scientists have developed a hypothesis or a theory, they'll know what that means. They'll have an understanding of that terminology and jargon. So naming and knowing kind of thing. So really, in essence, science is a way of thinking much more than it is a body of knowledge, because yes, there are some big ideas that go through this, but we know that science is, as it learns more, it changes and is refining their understanding over time. So the scientific methods are the ways that we teach students to think scientifically about the concepts or ideas they're learning about. So really, it's important for us to remember that we have our students in 1 year of their educational journey with us from kindergarten to grade 12, and that scientific literacy can't just happen in secondary or in high school. It's something that we're developing over time. And so it's a bit of a mind shift with this curriculum. If you were in the sessions yesterday, you know that it builds over grade levels, which is a little bit different than the legacy curriculum. Also, I often get asked from teachers that, how should we go about teaching the scientific methods? Do I teach it all in one, in September? Is it throughout? Well, again, the curriculum subject introduction gives us some ideas. So for example, it says, the science curriculum engages students in active investigation to build scientific knowledge. So they're building this knowledge through investigation and develop critical thinking skills. And we're going to talk today how the scientific methods are, in fact, a way of critical thinking. Secondly, it states in the subject introduction, students will have opportunities to integrate these skills into all other areas of the science curriculum. So yes, you can, like Edmonton Public has their scope and sequence where in September, they're being introduced to these skills. But the idea is that they're going to integrate these skills through all the other organizing ideas in order to understand those big ideas or concepts within those disciplines. Not only that, if we see the learning outcome in the other organizing ideas, it states students investigate. And yes, the slides will be available. There is a handout at the end as well. So any kind of template or graphic organizer will be shared out at the end. So students investigate. So what was created with the science consultants, Ted, myself, and our assessment consultant, was a science verb glossary to help you, and that'll be shared out at the end. So that tells you what learning outcome in this word or verb is found in, because that's what gives us clues for assessment, as well as your skills and procedures. So investigate means to use a process, right? We talked about that procedural knowledge to gain deeper understanding of those ideas. Well, that has been laid out in the grade 2 curriculum in the knowledge statement. So these are the steps, and I created this graphic organizer that we're going to work with today, as well as be shared out with you. And basically, this is the process. Now, it's not linear. We're going to kind of talk about that. Usually, scientists don't go around asking questions. They notice phenomena, they notice something or an event or something, and it makes them ask questions. They could maybe, so they're observing first, then they're asking questions, right? So it's kind of, but these are the steps, okay, that are every grade level should be going through. And the skills, and we'll talk about that, align with these steps as well. So a lot, as I mentioned, has changed since our legacy science curriculum in 1996. Okay, I always joke about this. That's back when Beyonce was part of Destiny's Child. But I also want to use the analogy that, science is something that I think we need to kind of develop an understanding of a little bit more. But what has changed is our understanding of how students learn in the early 2000s. And there has been some research in science education about how students learn science, and the United States has gone through their own reforms. There's lots of research, and I'm going to share some of that with you along the way, as well as the United Kingdom. And then, of course, PISA has made that definition, which our curriculum kind of uses as well for scientific literacy. So it's not just the curriculum that's changed, but our instructional approach to teaching science should reflect some of these changes as well, which I'll talk about. So what I'm going to mention quite a bit is a scientific lens that, I'm a proponent of integrating subjects and streamlining whenever possible. It's great. But we also have to honor the disciplinary literacy of science as well. So I'm going to bring certain things that are from a science perspective or a scientific lens throughout. So in the area of research and science education on how students learn science best was the question. Traditionally, maybe when we were in school way back in the day, some teachers were lecturing, or there was, we would read about the concept or watch a video about the concept. So they had classrooms learning the same topic, and one group did it that way. In our former curriculum, we did a lot of hands-on, a lot of like, here's your outcome with a series of hands-on investigations. And so they looked at classrooms learning the same topic with just hands-on only. But in a class that did both hands-on and text, and I think this is common sense, but what the research showed was that classrooms that used both hands-on investigation and text significantly outperformed those classrooms that focused only on text or only on hands-on. So how do we go about doing that? Well, traditionally, I think, and well-intentioned, we start saying, okay, here's a video on matter, or here's a video on force. So we're going to explain the concept to our students first, and then get them to go off going through the investigation procedure to understand it. However, the research in science education over the last 40 years has really shown that it's better to have students explore first and go through the investigation to draw their own conclusions, then synthesize that information with text for a couple of reasons. First of all, you're building that background knowledge through their experience. I kind of think of it like manipulatives in math. We want our students to we use manipulatives to get them to access abstract information, concepts. Although this seems common sense to us, we have to remind ourselves that we are working with 8 to 12-year-olds. So they're developing their understanding of the world as well. But they do have some understanding. So for example, a child can throw up a ball and knows that it's going to come back down. They can make that observation. What they lack is the formal vocabulary. So we can attach that when they go through that experience after, so then it makes more meaning to them instead of starting to give them the concepts. Another issue in science, and this comes out in the research, is there's dual meanings in science. So there's the everyday language meaning, and then there's the scientific meaning. For example, force. So a child's background knowledge might be, I'm forcing you to do your homework, or I'm forcing you to come with me. Whereas force in science is a push and a pull that results in a movement or a change in location of an object. So it can really, and we have a high percentage of ELL learners. So starting off with presenting the concept can be inhibiting students to learn. So and really encourage them to go through, see, make observations, and draw conclusions, and then attach those vocabulary to it as well. So in essence, it really isn't about you explaining to your students what the science idea is at the beginning. It's about you creating a learning environment in which they can construct the explanation. We want them to make the meaning and give it back to you so you can assess that. So now let's start focusing here on the scientific methods, particular to our curriculum. But I just want to take a step back because having gone through schools myself, and I kind of see it posters up of the scientific method with, observe and question and hypothesis. And we're going to really talk about hypothesis today. And again, this is scientific literacy. The scientific method in what we think traditionally is really narrow focus. Because again, as I mentioned earlier, there's different disciplines in science. So there's different investigation approaches. This is Jane Goodall in the field observing her chimpanzees. She can't control and have a manipulated variable. So she uses descriptive investigations. Some scientists look at systems over long periods of time, comparing weather patterns or climate, which we will do as well. And that's comparative investigations. But I think what we know of, especially from high school in the labs, is experimental investigations where there's one thing that changes and everything else stays the same, like that fair test idea. And so, for example, the question here could be, what seal is going to keep the maggots away from spoiling the meat? So we change only the seal, which is your independent or manipulated variable, which grade 5s and 6s get into. And then everything else stays the same. And the response is what we can observe, which is what are the flies, what's keeping the flies out. So in your other organizing ideas, they do hint to you. They'll say students will conduct a controlled experiment. So that tells you that kind of in that organizing idea, usually matter and energy, but it could be in other ones as well. And you can bring those in. It doesn't mean that you can't do that. But it's an awareness of that as well. So if you think of an investigation as an umbrella and there's different types. So they all have a purpose. There's a question that they're trying to answer, but an investigation doesn't always require the complete procedure. Okay, they can make observations and ask questions and predictions, and a hypothesis isn't necessary. So the term hypothesis doesn't come in until grade 6. So I'm going to talk to you, I'm going to repeat this. I don't think we should be using that term before grade 6 because it's going to create some confusion, and we'll get to that. Now, an experimental investigation also has a purpose and a question, and it involves testing dependent and independent variables to confirm or refute a hypothesis, more in grade 6, and it involves that classic scientific method. So now we're going to look at our curriculum and unpack it before we get into a little bit of processing work. So I know you know the architecture, but I do want to talk to you about the organizing idea. Again, we're gearing towards grade 12 with the organizing idea. So by the end, along the way, we're hoping by grade 12 that students will understand that investigation of the physical world is enhanced through the use of these methods that attempt to remove the human biases and increase objectivity. So that's going to be kind of developed along the way. So as I mentioned, these procedures were developed and sorted out in grade 1, just focused on questions and predictions and recording observations, but then grade 2 starts through. And we know that, like math or writing, they're not going to, just because they were taught in grade 2 doesn't mean that they know it, right? There's something that we might have to refresh along the way. And then in grade 6, hypothesis is added to that for a particular reason. So an important reminder before we start unpacking your grade level cusps, and I know you know that it's something we formatively assess, but having answered questions from the field at Alberta Ed, we were always reminding teachers to align the knowledge statements with the corresponding skill and procedure, that you don't read them in isolation, that they're pulled together. In the previous curriculum, they were written together, but regardless, as a consultant, I was always helping teachers. We have to analyze them. We have to pull them apart. What do they need to know and do and understand? So again, you need to kind of read them in conjunction with each other. And it's also important when they're looking at the skills and procedures to clarify what does the verbs mean, because that's what students do and that's what we are assessing. So we should have clarity in that area. So that student verb glossary will be very helpful with that. Okay, so we know that we have that investigation cycle with those steps. And each grade level has skills that they're going to maybe go in depth more into that step. Okay. And so I'm going to talk to you about what I did. We're going to go back to grade 3 because grade 3s are introduced to analysis of data. And that's something that's not easy. And it's something we need to continue to do in 4 to 6 as well. And then grade 4s add on to that with interpreting data. So analysis and interpretation go together, as we'll see. So I want to go back and kind of look at grade 3, and then that gives you an idea of what we're going to do with 4, 5, and 6 in Lumio. Okay, so in a moment, what'll happen is I'll drop in the chat and you click on it, you sign up just like Nearpod or Pear Deck if you've used that. And then I walk through and take control of, and you're going to see a presentation. We'll see grade 4, but we're going to start for grade 3. So their learning outcome, which they learn all year, is students relate investigation to building knowledge. So I've squared off in red the concept of investigation and building knowledge. Well, what the verb is, relate. Students need to connect how an investigation builds knowledge. Okay. Carrie, you've just raised your hand. Or was that an accident?
It was an accident.
Okay, no worries. Okay. So what we're going to do then is I'm going to show you the alignment, okay, what we should be doing in reading the knowledge statement in conjunction. So I'll kind of walk through this. So we'll start with the skills and procedures, collect data, we know that, using techniques to improve the accuracy of data. So the knowledge statements that kind of line up is the techniques, and they talk about improving that include, now again, that include, means we need to teach that, choosing appropriate tools. I would continue working on that. I'm going to observe caterpillars, clear a container, or, we're going to use a ruler instead of a meter stick or whatnot. Carefully measuring. We're going to have to continue that with volume and things like that, and demonstrating objectivity. Well, what is objectivity? So removing their personal thoughts. So for example, if the student draws a picture of a seed, they say the seed is small, that's actually a personal perspective, right? Because what's small to one person might not be to another. What's more objective is to say the seed is 35 millimeters, right? So when they're recording that, accuracy, of course, we know means correctness. Now, in analyzing data, they're expected to start doing that in grade 3. Well, it's laid out here what that means, and I'm going to show a classroom example after. Making connections, noticing differences, I'll highlight that. Discussing and collaborating. Well, scientists do ask, like, are you seeing the same thing in the data that I'm seeing? Compare the trustworthiness, and such as, we know means we don't have to teach all of them, but it's a sampling. And then analysis of data, so develop questions for further investigation. Now, in 4 to 6, we don't see anything about questions, but the assumption, again, it's like, well, they know their basic facts in primary, hypothetically, they should be continuing to work on that skill in 4 to 6, okay? So in a moment, I'm going to pull up the chat, and it's just going to take me a few minutes. When you click on it, a new tab will open, and it'll have my name like this, and it'll say your name. You can use my fake name, I don't care, and click join guest. I'm going to wait till everybody kind of gets in. And then when I see most people in, I'll take over and start doing the presentation. Where it becomes interactive is there's a sort of individual handout. Nobody else will see this but you, and I can pop in because it kind of gives me an idea of how everyone's doing. And all you do is click start. But once you click start, what you'll see is a screen with the investigation cycle and the grade level. We'll start with grade 4 and the skills because of each class, because I didn't have space for the knowledge statements. What you're going to do is you're going to read through the skills and decide where in the investigation cycle those skills from that grade level go to. And it's good to go back a grade and see what's coming up next. So for example, I would click on develop new questions for further investigation and drag that over to asking questions or predict the answer to a question, making predictions. It's not going to be straightforward, and this is an opportunity for you to kind of think about that onion piece. What are they diving deeper into? Okay, so yours may end up looking something like this. Now, again, I just want to highlight that the assumption is, like, you might not see certain steps that have any skills in it, especially as they move up in the grade. It might be more towards the end, hint, hint. Okay, but we will go over it. There isn't a lot of time, so I might give you 5-10 minutes per grade level to kind of do this, and then we'll walk through it after. It's just giving you that opportunity to think through this and digest some of this information. So again, I'm going to drop the link in the chat, type your name in and hit join guest. When you hit the link, it's going to pull up a new screen. And when we're done, we're going to come back to this presentation. Okay, so I'm going to pull up the chat and drop in the link. So just give me a few minutes. Okay. Okay, let me copy, Zoom. Okay, not that Zoom. Oh, here we go. Chat. Okay. Okay, I'm hitting enter. So you should, oh, I don't know why it went to Laura, so I'm going to put it back again. You should all be able to see it in the chat and hit the link and then be able to sign in. Okay. All right, I see. Oh, everybody's starting to sign in. Just give it a few minutes. I can see there's like 100 or so people in the session. So just look for most of that. Great. This seems to be pretty smooth. If you're on a phone and this isn't working, just follow along with us. And you can kind of think to yourself, I understand that might be a little bit more challenging. Okay, looks like we're kind of stopped there. Okay, so I have this, again, these are the steps of the investigation cycle from grades 2 to 5. Grade 6 will have generating hypothesis. So I'm going to walk through and then you'll have your own handout piece. Okay, so grade 4 begins with students investigate evidence and reflect on its role in science. So the concepts they're learning about is evidence and the role in science. And we'll talk later about the difference between data and evidence. But what they're doing is they're investigating and then they need to reflect on its role in science. Okay, that's going to help them when they get to grade 6. So again, we want to align our knowledge and skills and procedures, and they build towards the understanding, which is students understand that ongoing collection of evidence provides a way to expand and adjust previous knowledge. So starting on the right with skills and procedures in green, we want students to decide whether to collect descriptive or measured data during an investigation. So if we go to the knowledge in green, I've highlighted that for you. They explain what it is. Data can be descriptive and expressed using words. Quality. Now in brackets means, and I asked this question in my training at Alberta Ed, can we teach qualitative? And they said, well, if you're doing like the things that are in parenthesis, you're going off the curriculum because that's for the teacher to refer to. You can by all means teach it, but do not assess whether or not they know qualitative. What they should know is that it's the data that uses words is descriptive. Okay. Same thing with quantitative, that it's using numbers or measurements and things like that. So the narratives can also use numbers and counts, and that should be relevant, right, to what the observations that they're looking at or what they're looking for should be relative to the question that they're answering, right? And some observations aren't, and you need to consider all the ones that are relevant. Going back to the skills in red, interpret data collected from an investigation. This is a big highlight of what evidence is in the knowledge statement in red. Evidence is produced through interpretation of data. Okay, now if we look at purple in grade 4, they're introduced to the standard international units, interpret data using that. And then again in purple in the knowledge statement sort of highlights that for us. The final skill in yellow is represent evidence from an investigation in a variety of ways. Now, if we go to the knowledge statement, it says including, so that means they need to do written text, verbal presentations, graphs, tables, charts, diagrams, simulations, and models. So they need to use all those ways to kind of represent the evidence and communicate it out after. And we'll look at some of those ways. And another understanding statement is students understand that conclusions drawn during an investigation must be valid and reliable. So this is all about that. So if we start at the skills in green, it says collect reliable data during investigations. What is reliability? Well, the knowledge statement clarifies that. In order for them to make sure that they're collecting reliable and valid data, they need to know what that is, right? Reliability refers to the consistency of the data evidence? Is everyone, if we repeat this investigation or other people are doing it, are they getting the same data and evidence? The amount of data collected, just because we get one thing, does that really show this? So you should have a variety. We go back to the skills in red. It says draw conclusions using reliable and valid evidence from an investigation. So not only are they collecting, now they have to draw their conclusions, and that's an inference, right? So validity is in the knowledge statement, how accurately the data and evidence reflect what is described or measured. Okay, and then collect in purple in the skills and procedures, it says collect valid evidence by accurately using tools. So we looked at grade 3, that's where they were coming from. So we're continuing that forward, and they should continue that in 5 and 6. We know that that's, probably going to be something they're going to need work with. Discuss the tools that they're using before or after the investigation, and collaborate. I'm going to get rid of this. Hide floating meeting controls. There we go. Collaborate to evaluate the reliability. So that could be after, hint, hint. Okay, so that one's actually the same as what we just saw. So I'm just gonna go on to the next screen. Okay, so now you got the handout. So if you click in the handout, you should be able to read through I'm going to give you about 5 minutes or so to kind of read through the skills and procedures and see where in the steps you would see this. Okay. If you're on a phone, this may be a little bit more challenging, as I mentioned, but just listen along. So again, you can click on the statement and then drag it over to where it would be on the investigation cycle step. It's interactive now. Okay, good. I see Bob has said collect reliable data during an investigation is observing and recording data. Awesome work. Angela's asking about where we find the handout. If you're in Lumio, it's there. And you're following along with us, but if you're on your phone, that may be a little bit more challenging. Okay, we're getting close. I'm going to give you a couple more minutes. Some people are finishing up. Okay, I'm sorry that's happening, Jody. I'm not sure why. You might be on Zoom instead of seeing it in the second tab. Just double check, or if you're not on your phone. Yes, Lumio is free to use. I love it. It's your smart board. It's free for so much. Okay, it looks like most of you are finished. So I'm going to move forward. So it's going to move you forward. You're not going to have an opportunity, but this just gives you a start to think about. Okay. Yeah, I got a few people who've already handed it in and said, yes, I'm done. Okay, so I'm just going to kind of move forward because it's been about 5 minutes. All right. So in grade 4, so what you should see now is what I'm seeing, and that is that now what I've done isn't always set in stone. There could be an argument for different locations. Don't worry. Okay, so decide whether to collect descriptive or measured data during an investigation should happen during the planning phase. And it probably, that's when they should be thinking about this, right? Because they should be thinking, is this, descriptive or measured data? and that we're collecting, right? And discuss tools or technology used to improve the accuracy, right? Um, they could change their mind during, making after they make their observation and they have to go back. They may, is this, a great way of collecting it, right? Collect reliable data during investigations and collect valid data by accurately using tools, absolutely happening during the observation and recording stage. Now, drawing conclusions with reliable and valid evidence from investigation and representing it, interpreting comes after analysis, and we'll talk about that, and collaborate to evaluate the reliability. That can arguably even happen during the analysis or recording of observation phase as well. I put it more towards leaning towards conclusions, but that could happen there. Okay, so that kind of gives you like, they're going into a deeper understanding of these different procedures or processes or steps. Okay, so now we're going to move into grade 5, and we'll do the same thing with grade 5. You just need to click start on the handout when you see it. Okay, so in grade 5, the learning outcome that's summatively assessed at the end of the year, because this is a year-long process, is students investigate how evidence is gathered and explain the importance of ethics in science. So the concept is evidence and how we gather it, and ethics in science. And what students are doing with those concepts, well, they're investigating the evidence and how we gather it, and then they're going to explain back how important the ethics is in science. So it's something new in this curriculum. So we're going to walk through the CUS, and then we'll see how they kind of help. There's a lot of cuss in grade 5, but I don't have to sort of align too much in this one, because we want students to understand that investigations can be better conducted to understand phenomena, to better understand. That's why we're doing it. We want to understand why this is happening or what's causing this. So in grade 5, I mean, you can use phenomena in grade 4. It doesn't matter. You don't need to assess them on that. But in grade 5, they need to discuss technologies that give scientists the evidence, with evidence that's of things that can't be observed with the human senses. Because prior to that, they've been using their, senses to make observations. And so they define what a phenomena is, and that all the sorts of things that are going through this. But what I want to highlight is your matter. Because now in matter, they're introduced to the particle model. Well, that's too small. We can't see an atom with a naked eye. That's an example, right? Like what things the world is made of, in the world that we live in, our three-dimensional world. And sometimes the scale is too big, like the solar system. So we need things that we can make better observations, and technology with is towards that. And also we want students in grade 5 to understand that evidence is more reliable and valid when investigations are conducted in a way that limits bias. So we know from grade 4 that they were introduced to reliability and validity. So we're going to continue with that. And now we want students to identify biases that could influence an investigation. And so again, we talked about that personal, like even like the seed is small or the seed is large or things like that. And humans, as human beings, we are not aware of our own biases. And that's important for them to know that. So that's why we have these methods that are in place to kind of help remove that. And it's the best thing that we have, right? It's not perfect, but it's the best thing we have. So in this particular CUSP, we want students to understand that evidence from a controlled experiment. So now we're focusing and zeroing in grade 5 on what is controlled experiment. They don't need to know that prior. Okay, so from 1 to 6 or 1 to 4, but in grade 5, now they're learning about a controlled experiment can be used to make conclusions about cause and effect relationships between variables. We will get into that when we look at classroom examples, because it's a bit of a mouthful. So if we look at the skill and procedure in green, it says plan and conduct a controlled experiment. So that's this, if they need to plan and conduct it, they need to know what it is. So if you go to the knowledge statement, it says, it has one variable. We talked about that. Let's go back in red in the skills and procedure. It says identify the variables. Okay, so students need to identify them. They need to apply the vocabulary and use it in different contexts. And then, and we're going to get into this when we look at classroom examples, they need to evaluate the effect of the manipulated variable and the responding variable in a controlled experiment. What does that look like in the classroom? What does that mean, right? And so if you go to the knowledge statement, it's sort of always, it outlines for the students, they need to know what an independent variable is manipulated. I think this is something we have a big background with science. But finally, it says defend a conclusion based on cause and effect produced in a controlled experiment. So that goes back up to this skill and procedure that we're going to have our students do, goes to the understanding statement. I might have repeated this. I'm not sure. Oh, and also in grade 5, we want them to understand that evidence must be communicated clearly and accurately. So let's go to the skills. In green, discuss the use of diverse. Oh, controlled experiment is when the scientists control one thing. So like one thing changes, like if you were at the beginning of my session and I talked about the seal and keeping the magnets away, we only changed the seal. We change one thing and one thing only, and everything else stays the same. So it's not controlled by the teacher or anything. Great question. Thanks for asking it. So there's different ways of representing and communicating data, right? And so they need to know that there are. I'd say a lot of this is the evidence is clearly diverse representation of data is communicate evidence differently. And they need to use, so that gives them the criteria. This is your criteria for assessment. Do they use correct vocabulary? Do they include all the relevant data? Is it free from personal bias? And can it be understood by their intended audience? So other people, other lay people. And then in purple, if we go back to the skill and procedure, discuss potential impacts of evidence that is not communicated clearly. So what happens when we don't communicate this? So, that causes confusion or a lack of understanding, and those kinds of things in the way that it can be interpreted. Okay. And also, you guys have quite, oh, this is a repeat of the bottom section, so I apologize about that one, so we don't have to worry. Okay, so now you have the student handout, so just click Start. And now drag, these are the grade 5 skills, and see where the students, on what steps are they going deeper into the different steps on the investigation cycle in grade 5. Now, I'm just reminding you that there's some skill steps that they're sort of assuming that students know, and that's more so in grade 5. Okay, I've got about 3 of you who are finished, so just hang tight. We're going to give a few more minutes for those who might have just started. So about 2 more minutes. Okay, about a minute. So just kind of finish up. We will go over this. Just give you some time to think about it. Okay, so I'm going to move on and review this. Okay, so obviously discussing technologies that provide scientists with evidence that cannot be directly observed is observing the natural phenomena. But planning the investigation, plan and conduct a controlled experiment. Identify the variables. They should be identifying the variables in a few places before they do it, okay? Because the responding variable is, what am I observing, right? What am I measuring or observing? And then, of course, they should know when they're planning what are the manipulated variables. They can also use that vocabulary, during observing and recording data. We want to reinforce that vocabulary. And when they're analyzing the data, absolutely. Identify biases. They should be doing that before. You could arguably say they can do that for observing and recording data and analyzing data. And of course, they're going to apply that vocabulary during the planning phase and during the observing and analyzing data phase, right? They're going to be talking about the independent and manipulated or responding variables and the controlled variables. Now, when they are comparing for clarity and accuracy of evidence communicated is the key. It's okay. Don't worry, Katrina. I know this is just kind of giving you some thinking time, but that's why we're going over it after. So no worries. For the representation of data, discuss potential impacts of the data if it's not. So that might be happening, and during the analysis and the conclusion phase. They should, of course, defending a conclusion is reaching conclusions or discussing that. And evaluate the effect of the manipulated variable is going to happen during the analysis and, of course, close to reaching a conclusion. Okay, examine the importance of scientific ethics. That could happen arguably during the planning phase or observing and recording. That can happen throughout different phases as well. So, they could be reflecting when they record their observations, is this ethical, right? They should think about that prior. So make the assumption here is that, they've been developing questions in grades 2 and 3. They should know how to do that and continue to do that as part of the planning. They should be making predictions. And all of those things are sort of assumed, but there isn't a deeper skill development in grade 5, if that makes sense. Okay. If it's cut off, drag the skill in a little bit more and it might help you with the reading it. We're going to move on to grade 6 now. Okay, so now grade 6 is learning outcome states. Students investigate and describe the role of explanation in science. So the concept of an explanation or a scientific explanation, and we'll see some classroom examples after. But what students are doing is investigating that, learning about what an explanation is, and being able to describe an investigation itself, or a scientific explanation, sorry. Okay, so we're going to walk through the cusps. Students understand explanations are used in science to answer a scientific question. So they might do little investigations to understand bigger ideas in science, like for example, I mean, grade 5 keeps coming to my mind because I was working, I'm teaching that when I'm going back to school. So that was coming to my mind about buoyancy and gravity. So they might have a bigger, or density even, right? So they might have a bigger overall question, but they might do little investigations along the way where they draw conclusions, right? But the scientific explanation answers the whole thing about the bigger concept. So if we go to the skills, it says discuss the role of scientific explanations. So they need to know what it is. So it's, you know, it's making sense of that phenomena, right? Answering the why this is happening, and they are testable. And that's why we do an investigation, right? We want to understand it, but it may not be something we get the answer to, or what we think is the answer. If we go back in green, it says develop and test a hypothesis based on a scientific explanation. And we're going to see the classroom example of this and really work through this. Hypotheses are proposed explanations. They're not prediction. There's an element of predicting in it, but it's different. And in conducting an investigation, and hypotheses are based on prior understanding and knowledge. So you don't have to just do a hypothesis in a controlled experiment. You can do them in other investigations as well. But they do lend themselves nicely to a controlled experiment. In the other cusp, it says students understand explanations in science are communicated in various ways. So if we start with the skills, interpret multiple forms of text that offer explanations of the natural world. So I've highlighted a couple of things in red. And then also the third skill says construct digital or non-digital graphs and tables using proper labels, legends, scales, and titles. So we can be teaching that in 4 and 5, but we're really going to zero in and assess that in grade 6 as well. So 4 and 5s, you can help grade 6s with us, because I think that's in math as well. So if we go to the what's red in the knowledge is quite high, because First Nation, Métis, and Inuit share explanations of the natural phenomena through these ways. So I think of sky science, right? Like they have their own explanation of why the constellations are what they are, right? Through stories and legends or other means. Now, scientific explanations incorporate a variety of texts. Now, we know such as means it's a sampling. So they can do visual forms, and they give you examples of graphs, tables, diagrams, and models. And we're going to see examples of that. And written text, and we're going to see example of a written scientific explanation, and verbal presentations. So we want in the skills and procedures students to communicate explanations using appropriate digital or non-digital tools. So both. So they could create models using, that could be where they're, you know, through Scratch or things like that. Or they can draw the models, or they can write about them, and they have to consider the audience. I'm looking at the scientific the knowledge piece. So using vocabulary, having some detail in order for the audience to understand, just like we would, you know, you want the audience to understand a story, right? Thinking about your purpose and intent. Students, the other cusp is students understand that science is a self-correcting way of knowing about the world, where new evidence can change our understandings. So if we look at the skills and procedures here, discuss processes that can be used to validate evidence and explanations. So evidence, if we go to the knowledge, it says evidence and scientific explanations are subject to further investigation to make sure they're valid. Okay, so in grade 4 and 5, they've been learning about validity. So you can see that's continuing through. Further investigation involve a variety of process, again, such as means a sampling. So maybe continual collection of different evidence over time from different investigations. Reading about discussions and debates in the scientific community, using new technology or methods. The other skill says identify explanations of the natural phenomena that has been refined as new evidence has been revealed. So they give you in the knowledge statement in green, it sort of gives you some examples that they used to believe the sun revolved around the earth when actually the earth revolves around the sun. So that's an example of science self-correcting. They did that quite a bit during COVID, by the way, as our understanding, and even long COVID, as our understanding about that changes, so does our, you know, it self-corrects what we thought. Different tastes are detected by, you know, so different things, they give examples. And I like this one. One conflicting study is not enough to change a scientific explanation, because you need multiple forms of evidence to strongly indicate that. Okay, So now again, a lot of the steps have been developed along the way, hint, hint. So looking at your skills and um, seeing where do they correspond on the investigation cycle, just think about that. Okay, where are they going deeper in grade 6 now with scientific explanations? Because they're explaining back, answering the question. So I'll give you about 4 minutes to finish this because we do have to move on. Trina, it might be on your, check your tabs. You might be back in Zoom, but it could be in your tab. Okay, quite a few of you are finishing, so I'll just give you like a minute or so to finish up. That's a great question, Jane. At this point, there isn't sort of a scope and sequence across the grades. But that's something that we could develop as well. Unless Ted, have you done a scope and sequence?
I've done just a brief one pager. That was one of the slides. Jane, were you on my slide or my presentation yesterday? If you were, there is a slide associated with the scientific message near the end of the slide deck. If not, we can certainly make that available.
Okay, I'm going to move forward. Just this gives you again an idea of sort of where things are at, and I'm going to go over it to kind of review that. So I'm going to move on. Okay, so discuss the role of explanations can happen during their observations of the natural phenomena, and it can happen at the end as well. So if you put it at the end, don't worry, that could be correct as well. Obviously, develop and test a hypothesis based on a scientific explanation is generate a hypothesis, and it corresponds with that step. So basically, by grade 6, they've gone through most of the investigation cycle. So the idea is that they know this. Okay, and we know that like story writing or like math, that's not always the case, and you're going to have to review different skills with different students. But the idea behind an explanation is answering the questions. They've gone through, they've gathered all of their evidence and data, they've analyzed their data and interpreted. So now they're kind of answering that question. Okay, so create scientific explanations that can happen because it is a hypothesis there too. We'll talk about how to do that. Discuss observations and measurements used to create the explanation. Well, the explanation is happening at the end. It's answering that question using all of the, evidence and data, the data that they've analyzed and interpreted. Of course, they have to think of the audience and how they're communicating this, using digital or non-digital means, and refining changes over time. And then discuss processes that can be used to validate the evidence. That can also arguably happen during the phase, so that's okay there too. And for interpret multiple forms to explain it. Well, that should be after they've drawn their own conclusions, and then look at them multiple ways, and then there's argumentation that happens, right? And evaluate the trustworthy of it. This all kind of is happening towards the end. So I'm going to close out of Lumio and we're going to go back into the actual presentation in Zoom. So don't worry, it just kind of closes it out automatically. And then you just go back to the presentation that we began with as you're in the tab that's open. Okay. So we should all be back into, it says instructional time on my screen. And we should be back there. Okay, so I pulled this off of Alberta Education because sometimes I think there's confusion about, time and that it's the same as social studies, when in fact, actually, it's the same amount of time as math. And we know that integration can help. So in ELL, you have your vocabulary organizing idea, which talks about tier 3 words, which is academic words. So that can come in. Oral language, that piece can fit in because they should be talking in science as well. As informational text or even narrative text sometimes can be used in science as well. So there is ways of integrating to help you meet the time requirements. And I'm sure people will talk about that in other sessions as well. Okay, I went backwards, so I'm going to go forwards. Okay, so now this part of this final part of the session is we're going to look at, well, what does this look like in our classroom? And so from the investigation procedure cycle, I'm going to zero in on Lorraine, please check your tabs and go back to the original tab. You probably have 2 tabs, so that tab should be gone. Okay, I'm going to look at analyzing data, interpreting data, cause and effect relationships, scientific explanations, and what is the difference between a prediction and a hypothesis? Why before grade 6 should we really avoid that language? Okay, so now analysis, just because it starts in grade 3, it should continue all the way through to grade 6. Okay, just like their basic facts or adding and subtracting double, triple digit, right? Interpreting the data begins in grade 4. So an analysis, interpreted go together. Okay, so we're going to start talking about that. So let's talk about what is data. That's laid out in the grade 1 knowledge statement where it says observe in this curriculum. And we're going to go from a science lens. Observations can be recorded as data in many ways. So data is recorded observations, okay? And I'm going to show from a science lens what we mean. So this is Charles Keeling. He's a climate scientist. You may have heard of the Keeling effect or the Keeling curve. And he won a Nobel Peace Prize for the way in which he gathered data and represented it to measure the amount of carbon dioxide in the atmosphere on Mauna Island. This is his data. It means nothing. So in science, data is not information. So in other subjects like social studies or things like that, data can be information, but not in science, right? This means these are just a sets of numbers. It's recorded observations, right? When we analyze and interpret the data, meaning is provided to it and it makes more sense. So we get the meaning or evidence or the information from it, right? It's not information in this form, but a graph allows us to see, oh yes, these are the ups and downs or your annual cycles, but over a series of time, you can see patterns or trends when you analyze it, that it's increasing the amount of carbon dioxide in the air is increasing. Okay. So again, this is scientific literacy. This is something we want our students to understand in science that sometimes is confused, right? That I had mentioned earlier. So in grade 3, they've separated analysis and interpretation. Okay. So in grade 3, they're learning about it and they're going to continue in 4 to 6, right? So again, our science verb glossary talks about what it means to analyze. So this is the learning outcomes in all of them. And the skills and procedures in grade 3 and 4 have analyze. So analysis is to break down into parts to see how it works. So, it says making connections to previous knowledge. Well, predictions are based on your prior knowledge. So does it confirm our prediction? And we're going to notice different changes and comparing for, asking questions and discussion. So we're going to use a grade 4 example of magnetism because it's very simple and straightforward. So let's say I begin the unit by giving students, partners, trays of objects and a magnet and say, okay, what sticks to a magnet? And they're probably gonna have background knowledge with this. This is pretty simple. And so they collect their data and record it, okay? Now I want them to analyze it. So a question I can ask or they can write about is, what similarities do you notice? What patterns? Because in science, it's regularities, what's repeating and what's different, the noticing the changes. So a student response, let's say they think, pair, share, they can write about it, that's up to you. The student response could be the similarities is all the objects that stick to magnets are made of metal material, and the objects that do not have metal, that's the difference, do not stick. So this is pretty straightforward, right? And then I can, a question could be, well, let's look at our predictions. Does this confirm or, our prediction was correct or refute, or was it incorrect? And then the student, of course, because they have so much background knowledge with this, well, my prediction was correct because I played with magnets on the fridge and I've seen that they stick to things that are metal. Okay, so that's analysis. Well, now what's interpretation? Well, in our science verb glossary, again, this is from Science Lens, interpret means to use reasoning to make sense of meaning, right? We saw that graphs help with that, or text or a set of data. So how could it's almost make common sense, but the question would be, well, what does the data show us about what is magnetic? So now I'm using a science term and they generalize out metals are magnetic. And that might spur them to ask, well, are all metals magnet? So let's zero in now with metals and test that, right? So that could be kind of a way to go forward with this. I'm going to show, this is a colleague in my ambitious science teaching group in the States. She really thought this was cool. And I think this is something we could do is to improve data literacy, is to have data talks where they're looking at what happens to the Arctic sea ice over time. And they're having a conversation and looking for trends in the graphs that are already published. And they're doing some analysis and seeing that and sharing that out. So I just wanted to kind of point that out. Now, grade 5, when they're having to deal with density, which is like mass and volume creates density, and they're directly comparing two solids, like this is copper and aluminum, and they're the same volume, graphs are going to help with that interpretation. What trends are you seeing? What seems to be repeating? What seems to be happening? And kind of working with that. And then what does this mean? So, change in density and those kinds of things. Okay, so in grade 4, we hear the term evidence. So what is evidence? Well, evidence is interpreted data. So meaning has been given to the data. So it's been analyzed, broken down into what's the same, what's different, what repeats, and then it's generalized out, or that they can see kind of the trends that are happening, okay? So now we're going to go into, yes, a handout will be given with all the links to the glossary and the procedure cycles for each grade, with a summary of that, and some of the graphic organizers I'm about to share. Okay, so in grade 5 and 6, cause and effect is an important thing in science. And it gets to sort of what grade 6 is kind of getting at as to the explanation of the answering the why, right? They go through an investigation in order to answer the why, to give a reason for it. However, in grade 5, we're going to look at that understanding statement. Grade 4, I'm going to talk to you a little bit about this too. So just hang, even though we're learning about grade 5, it still connects to you. Evidence from a controlled experiment. So that's your parameter. They're going to really zero in on controlled experiment in the scientific methods, okay, can be used to make conclusions about cause and effect relationship between the variables. So let's kind of unpack this a little bit. We know that evidence is interpreted data, and a conclusion is using evidence to make an inference or to kind of, to answer the question that they're investigating. Small scale investigation, we have bigger ones. So I have defined here cause effect relationship. So I'm going to start with effect because that is what we see in science. That's what's observable, right? So it's the event that occurred. It's because of a cause. And in a controlled experiment, it's the dependent variable. Okay, that's what we see the result, right? The maggots, what were they doing? They stayed away from the seal, but they were in the open container and they were in the cloth seal. So the students should be thinking, what happened? What did I see? What did I measure, right? Now, the cause is the thing that gives rise to the event. So it sort of is what's creating the effect. Now, in a controlled experiment, in our curriculum, it states it's the manipulated variable, but we have to be careful. Manipulated variables don't always cause what we see, okay? But I think for simplicity, what we want our students to think, because these are thinking skills, why did this happen? Now, I'm going to jump from relationship to system because we're looking at the relationship between the variables, right? And I'll talk about what that means in science. But a system in science is what we're discussing or the boundary of what is being investigated. So for example, we've got the whole human body, right? But we're talking about the digestive system or the nervous system. But even in physical science, they talk about systems as boundaries of what is being investigated. So a relationship is that interconnections between the parts that make up a system, and that is unobservable. So this will make way more sense when I show you the classroom example. But it is really getting to that depth. Like if we talk about surface deep transfer, we're getting to the deep piece of the learning because it's connecting to the scientific concept or the big idea in science. So what the students are thinking about when they're thinking about the relationship between the variables is not only why did this happen, but how did that cause make the effect happen? So I'm going to show you an example in a moment because I talked about this. I'm going to jump that one. Okay. Again, I'm going to just zero in on the skills and procedures because that's what we're assessing. So we should know what those verbs mean. Evaluate is to determine the significance and importance or the quality of the manipulated variable on the responding variable in a controlled experiment for grade 5. Defend a conclusion. So conclusion is like the answer to that, is to support using evidence and reasoning. So they're higher level thinking, okay? So when I see, in Pinterest or, those kinds of things, I see these graphic organizers, and that's okay. That's your surface level if you're in TED session of learning, and they need surface first. They need to, but that's identification, right? They identify the cause, they identify the effect, and that's okay to start with. But my question to you is, well, if they just do this form, how are students evaluating the effect of the manipulated variable on the responding variable? How are students defending conclusions based on that relationship, the connection of the parts? So I'm going to show you a graphic organizer to work with to get to these two skills and procedures. That is in a handout. So this is an investigation because it kind of brings it to life. So students are investigating how does weight, this would be from your energy organizing idea, how does weight affect an object's ability to float or sink? So grade 5, if you are given money, I would purchase a Newton or what's called a Newton or spring scale. because that is probably the best visual of gravity pulling down on the amount of something in an object. In grade 6, you could use it for different things. You could use it in your energy organizing idea for a spring and the tension between from the spring to how it attaches. That could be something that you guys could use it for differently. But in any event, in this investigation, what they're doing, the boundary is they are taking a bottle of sand, empty bottle of water. They're filling it with different amounts of sand, and they're going to measure. That's the different amounts is their the force of gravity pulling down is their manipulated variable, and the response is, does it sink or float? They're going to measure that with the ruler. How submerged is it in water? So they need some prior knowledge, obviously, and this is just because they can regurgitate to you that weight is the amount of gravity pulling down on an object. They don't fully understand that. That's why I like a spring scale, because it shows pulling down as best as possible, because hint, hint, gravity is unobservable. We can't see the force of gravity working, right? So we'll get to that. So this layout, basically, and you'll get a template to this, just gives them the blank squares and they can fill it in. So what are we in? What's the question? What's the system, which is the bottle filled with sand in water, placed in water? So the effect is what we start with, right? So, they've measured it and does it float or sink is the effect, right? That's a responding variable. And then they've measured it. When it has 0, now it's measured in newtons, weight is measured in newtons. So at 0 newtons, it was floating and it was just 3 centimeters raw. So we consider that floating, right? And then 25, and you can see this. So if we're going to get them to evaluate the effect, we should get them to analyze the data by asking the question, look at the data. What is the same? What patterns or regularities are we seeing between the cause and the effect? Right? Is it predictable? Because patterns are predictable. Okay, so what the students could think, pair, share, they could write about this. They could say, well, I see that as the weight is below 1.0 newtons, the bottle was floating. And when it got to 1.0 newtons and above, it sank to the bottom. So I predict that if we add 3.0 newtons, it would sink, right? That's predictability. So, but then they have to defend a conclusion based on the cause and effect relationship, right? So this graphic organizer, and I'm not going to take credit for either of them, they come from the wonder of science. And this will be shared out because I can share it. These numbers tell the students what to start with. So we start with the effect. What happened? And then they can use this on Google Drawings and, kind of fill it in. The cause is what was caused. Why did this happen? And then the relationship. So how does this happen? How did the cause create the effect? So I'm going to show you an example. So the effect was that it was floating in 2 centimeters of water, and the cause is that the buoyant force of water is greater than the force of gravity acting on it. That's okay for them to tell you, but to actually show you how does this work in science and that relationship between the two, they use a diagram. So they can use arrows, and you can see the thickness of the arrow showing the buoyant force of water is greater, right, than the empty force, that gravity acting on the empty bottle, right? Inversely, it would be when the force of gravity is greater than the buoyant force of water, it's going to sink, right? So then they can kind of talk about that and generalize that out. So it really helps them. And in grade 6, this would help you with scientific, preparing for a scientific explanation. So in summary, the effect is what we see. It's observable, and they'd start with that. The cause is the why. Now it's looking at the manipulated variable to ensure that. But the relationship between the two is the science concept, right? They can't see the force of gravity or the buoyant force of water, but they need to be able to explain how that works. Okay, so you can see the depth of understanding. They're going from surface to deep understanding here of the concept itself. Okay, so now that leads us to the final piece, is grade 6's scientific explanations and, of course, hypothesis. Now this is getting to the why this is happening and showing us that scientific methods is a form of critical thinking. Okay, so in our understanding statements, just to refresh us, explanations are used to answer the scientific question, and scientific explanations are constructed using data and evidence. So they've been building that from grade 4. And again, the different forms, and I'm going to highlight that. The visual form, we just saw a model of that in the cause and effect relationship in a way. And we're going to zero in on the written forms as well. So there has, again, because of the research, you may have heard of this. There is an instructional framework to help students write scientific explanations or make scientific explanations, could be, even orally or, visually. And this is a framework called claim evidence reasoning. I used this in my own grade 6 classroom. So I'll share some examples. And a claim is an answer to a question. The evidence we know supports the claim or refutes it. But in this case, if they're making an explanation, it should support the claim. And the reasoning should explain how the evidence supports the claim. So it should be grounded in that scientific concept, just like we saw with gravity, the interplay between gravity and the buoyant force of water, about the object floating and sinking. So what I'm going to show you is a video from Paul Anderson. He does a wonderful job explaining this and how to do this. So hopefully I tried to skip the
if you're a web designer, here are 4 Wix Studio features you gotta know. Hi, it's Paul Anderson, and in this video I want to talk about CER. It's a framework for making explanations in the science classroom. It's a skill that teachers should give their students, and students should have if they want to improve their scores on lab write-ups, on essays, or on big exams. But before we talk about CER, let's talk about science in general. In science, what we're doing is gathering evidence through investigations of the natural world. We're then coming up with explanations that are critiqued over time. But unfortunately, a lot of the time in a science classroom, the investigations are developed by the teacher itself, and the students are just going through a cookbook lab, and so we want to avoid that if we can. But also, we spend too much time on the investigation itself, on the variables and controlling the variables. And then when we get to the end of coming up with an explanation of what we learned, we kind of fall down on that point. And so the CER is a framework that makes this explanation making explicit. It was developed by Dr. Kate McNeil and Dr. Joe Krychek. I'll put links to some of their material down below, but it's an acronym. The C stands for claim, the E stands for evidence, and the R stands for reasoning. Sometimes you'll hear rebuttal added at the end of that. That's looking at somebody else's claim, evidence, and reasoning. But this is my model for how claim, evidence, reasoning works. Claim is an answer to a question that's asked. Evidence is going to be what you gather, empirical evidence that's gathered in the lab or through research. And then reasoning is going to be a logical connection between the evidence and the claim that you're trying to make. Now, students will generally do really good at the evidence gathering, but they fall down when it comes to this logical connection. And so a good tip is to make sure that your reasoning is based in some kind of a scientific definition, rule, principle. That's a way that in science we can all agree on that. Now, what should a teacher provide? A teacher should simply provide a good question and a way to answer that question. So let's say in the science classroom I give my students a bunch of dice, but they're different looking dice. They're skew dice that look like this. And I ask them the following question. Are these skew dice fair? Now, they could start gathering evidence right away. They could roll the dice a bunch of times. We could measure the dice, look at their center of gravity, maybe measure all of the sides to make sure that they're all the same. But before we jump in and start doing evidence, make sure that you've actually framed the question and you understand what's being asked. Make sure that you could define everything that's in this question itself. I'm sure you know what skew dice is, but are we all in agreement with what it is to be fair? Well, let's define it. Fair is this idea that each side has an equal probability of ending up on top. Now, once we have that definition, you can use that in that logical connection. Let's get to an actual science question that we could answer. Is air matter? That's a question you could answer in the science laboratory. Before we dig in and start gathering evidence, however, we should frame the question and make sure that we understand what every term in there means. So what is air? Air is an invisible substance that surrounds the earth. What is matter? Matter is anything that has mass and takes up space. What else do we know about matter? It can be neither created nor destroyed. So sometimes it's helpful at the beginning to get all of these listed out so that we can use them at a later date. Now we can use a form like this to do our claim, evidence, reasoning. Claim is going to be an answer to the question, but generally we don't start there. We have to start by gathering evidence. So perhaps I take a balloon, put it on a scale, and then I fill up a balloon and put it on the same scale. I'm trying to show that there's an increase in mass. And then maybe I want to look at the takes up space side of the matter. Maybe I take a bottle filled with water, pump air into it, and I can displace some of that water. And so now I can make a claim. Yes, air is matter. That's going to be my claim. I've gathered evidence, but now how do I do the reasoning? Well, the reasoning is easier if it's tied to one of those scientific definitions that I had before. So let me read you my reasoning. The mass of the balloon increased when air was added, indicating that the air had mass. The air displaced a volume of water, indicating that the air also has a volume. Since matter must have both mass and volume, my evidence suggests that air is matter. That reasoning part is what we hope our students will start to write, and they never do. Generally, when they're doing a lab write-up, they simply tell us the evidence they gathered over and over and over in more detail. But what we really want is a connection between the evidence that you gathered and the explanation that you're trying to make. Now, we could do a rebuttal on that. We could say, well, let's look at the evidence here. You blew this up, so that's air coming from your lungs, so it's not coming from the environment, so that could impact it. Maybe it's water there. And also, it looks like there's air right here. And so are you really measuring air, or are we measuring air pressure? And so now we can have argumentation, or we can talk about the evidence or the reasoning. Now, all you do when you're doing labs that use claim evidence reasoning is just give them a good question and a material to answer the question. I could give them a bunch of magnets, and I could say which of these is the strongest. Give them a bunch of paper clips, rulers, whatever, rubber bands, washers, and they have to answer this question. The first question they should ask you as a teacher, however, is let's make sure we frame the question and define everything inside it. What is magnetic strength? And if we say it's a measure of the attractiveness or attractive force between a magnet and magnetic material, do we know what a force is? Once we have all of these definitions out there, it's easier for you to do a claim evidence reasoning. Now, these are pretty low-level science questions. We could do it in a...
Okay, so he goes on into a high school level, but I really thought he did an excellent job of sort of guiding us through that. And these are examples from my own classroom. Please indulge me. I'm going to be going over time a little bit today. Indulge me 5 minutes. But anyways, these are examples from my own classroom with the old curriculum. And this boy was a great writer, but what is helpful is to have the students go back and highlight the evidence and especially their reasoning. Do they have it in there? You might want to use a guided practice so they can do claims really well in evidence gathering. Maybe make it a guided interactive writing piece where they write the reasoning with you, and then gradual release of responsibility. So I do share some lesson ideas and some graphic organizers in my handout. I really liked this one because it forces the students to connect the evidence to the concept, the science concept, and then how does it support the claim? So these are some organizers to help them think through some of these ideas. So lastly, I do want to get to hypothesis because I really want it to be clear why we should probably avoid using that unless we're teaching grade 6. Okay, so what's the difference between a prediction and a hypothesis? Well, a prediction is an anticipation of what we're going to observe in an investigation. So it's what we're going to measure. And so for an example, it could be tomato plants grown with nitrogen fertilizer will grow faster. We can observe that they're taller and have more leaves than tomato plants grown without nitrogen. Okay, all those 3 things are observable. A hypothesis is stated in our curriculum is a probable explanation. So we went through this, it's a claim. Okay, it's a claim that they're going to test. That's what a hypothesis is. So for example, it says plants need nitrogen as a nutrient to grow. So it's broader, and it does include some science vocabulary. It's broader, and it's there's nothing there to observe. We'd have to see, well, what would be the result? So I'm going to walk through the final piece of this is to walk through. Oh, sorry. The back. I want you to. Really important to for our own background knowledge. What is the role of a hypothesis in science? Why do they come up with these? The role is yes, it answers the why, but secondly, when scientists go out and do experiments or investigations, and they make hypotheses, if they can be refuted, absolutely that happens, and it isn't confirmed. But if it's tested and confirmed, and other scientists might repeat the same experiment or investigation, or they might do their own, but have the same hypothesis. Once there's a numerous amount that are tested and confirmed, that idea becomes a theory. So in science, a theory isn't just an idea. A theory is substantiated with an amount of evidence to it. So its hypotheses are quite important. The literature and research about teaching hypothesis cautions against, I think, what we know and our secondary colleagues might use is using if-then formula, because if-then is a prediction. So if I add nitrogen to the soil, then, the responding variable, what we observe, right, is a prediction. Adding because does push it to a true hypothesis, but what the literature shows is that oversimplification of doing that creates confusion for our students. And I think that's why, in general, many people who do not have a science background are confusing. Like, I see grade 2 students are doing a hypothesis. No, they're not. They're doing a prediction. So I think that's many reasons why many of us are confused about the difference between a hypothesis and a prediction. So what you could do, again, they observe a phenomena. So what did you observe in the tomato plants? Oh, think, pair, share. Okay. Oh, I noticed that plants labeled with nitrogen were taller, darker, and had more leaves. Wait, great. What hypothesis do you think might explain what you observed? Oh, I think if I add nitrogen to some plants, then they will grow taller. Okay, what you shared is a prediction of what you think will happen or you observe in an experiment. Why are you able to make that prediction? So we're pushing them to go deeper, broader, because it looks like nitrogen helps plants grow better. They could think, pair, share. They could be writing this. That's more like it. What you've just given me is an explanation, an actual hypothesis, but I think we can even make it better. For example, what we call those materials that organisms take in from the environment that help them grow is nutrients. Knowing this, how can you improve your hypothesis? Think, pair, share, or write it. How about nitrogen is a nutrient that helps plants like tomatoes grow, or helps plants grow? So you can see it's broader statement generalizing out to all plants, not just to specific experiment, and it's not what we're observing. Sounds great. You got a testable explanatory hypothesis. Now let's design the experiment. We won't go through that. So thank you for indulging me. If you want it, some of you can hang back. I do have a question and answer period, but the key ideas I want you to walk away with is that students need a blend of hands-on and text. Explore before explain. They need that concrete experience first to make sense of the science ideas and draw conclusions and then attach the meaning to it. But when you use resources that give you some hands-on, really think, does the hands-on activity include minds-on? And that they should be also reading after to obtain important information. The science methods are the thinking that students do to understand the concepts from the organizing idea. So going through the process to draw conclusions first enables students to build knowledge and develop conceptual understanding when they start synthesizing and attaching deeper meaning later. The skills and the science methods taught in one grade need to continue in the subsequent grades. I think that I was really harping on that. Like, asking questions starts in grade 2, but we should continue that on into grade 6. Same with making predictions, analyzing and interpreting data, and the causal relationship between the data goes from 5 and 6.